Thank you, Jay. That was not what I asked you. So I actually asked Jay to say that I was working in France and I didn't have a French accent. But I don't. Okay, uh, so my name is Luan. I'm working in INRIA. INRIA is a French institute. The city where I am is Bordeaux. It's a very nice city. And today I'm going to present one of the works that we are doing in my team. The name of the team is TADAN. And it's called IOPS. It's the IO Performance Evaluation Suite. I don't know how to use a microphone, sorry. Is it good like that? Okay. Okay, so first thing is, everything that I will show here is actually a secret from the French state. So I need you to turn off your laptops and pay attention. No, it's a joke, don't worry. Okay, so before I start, I actually want to give you the definition of IO performance characterization, the definition that I have in my mind, right? What is a IO performance characterization? So in this context here of the tool that I want to present, an IO performance characterization is actually to look to the cluster, to the storage system, and see what happens when we change the parameters, okay? So quick explanation about I/O. We have these compute nodes, and then in these compute nodes, we put our applications to execute, and when it's time to do I/O, usually in a cluster, in a HPC system, we have a parallel file system, right? So that's what I try to represent here in the figure. So in this parallel file system, we have object storage targets, or OSTs. And when we are writing a file, actually what happens is the file is break in same size chunks, and then the application send it in parallel to the parallel file system. And that's the way we have performance. We increase the performance because of this parallel thing, okay? All this process is called striping. So as you can imagine, we have several parameters that can affect I/O performance. For example, the number of compute nodes can affect I/O performance. The number of processes that are doing I/O per node can affect it. The file size and the number of storage targets, okay? All those parameters, somehow we can control it. We can define the number of compute nodes. There is a way to set up the number of storage targets, and so on. And what I'm calling I/O performance characterization is basically this, right? I go there, I get a benchmark, I set up some parameters, and I say, okay, I want to study what happens when I change the number of storage targets. And then we have a graph, very beautiful graph, like that. That shows the bandwidth, right, according with the number of storage targets. And we can do this for all the parameters that I show to you. And that's only some of the parameters. We have more things that can affect the performance. Right? And why? Why that's important? That characterization is important. So here, some examples, some reasons, some motivations. For example, because I want to know what's actually my peak performance. What's the peak performance of my I/O system? And why I want to know that? Let's think about an example. Let's say that you go there and you decide to buy a new machine. And then you have the theoretical performance, right? But what's the parameters that you need to reach this theoretical performance? You have to do the I/O characterization to know this. So basically, one of the examples is to validate the recent deploy system. Another example is actually one of our motivations is when we need to do an I/O test, an experiment, we actually need to know what we need to have to reach the peak performance. Let's say, for example, that I want to study interference. So I have to go there, decide my parameters, put the application to run, usually a benchmark, to create this interference. Another example, to define the best for the application. So I have a cluster and I want to identify what I need in terms of application, what is the I/O pattern that I need to reach the peak performance. And then I can decide, okay, I need to work on my application to improve it. And finally, to identify the abnormal system behavior. And turns out that this last example here is our main motivation. all this work, all this tool that I'm showing for you today is actually, it came out from a paper that we published in 2022. And I think that paper was actually presented here in this conference in 2022. It was 2022, Jay? Yes. So in this paper, we had a postdoc, and he had a lot of work to do a series of benchmarks to do a characterization in our cluster. And one of the results was actually this one, in the first figure. What that result shows is actually that in this system, all the application, times to times, had different I/O performance. Sometimes they have a higher bandwidth. That's the case, for example, here. Sometimes they have a low bandwidth. And that was actually a abnormal behavior. There was one line, actually what I start to develop to help me on this task was actually what becomes the tool that I am presenting today. So the tool is called IOPS. It's a very nice name for an I/O tool. And this tool now, since the beginning of this year, is actually part of the stack of Exadost. Exadost is the project, the French, how can I define this? Is the storage part of the NumPX project. And the NumPX project is the French project to work on the development, not from the machine, but development of the tools related to the exascale machine, okay? It's a definition of Exadost. And then what IOPS does is actually using benchmarks, right, to do this characterization that I explained to you. And the focus of the tool is on different combinations of parameters. So the tool is very simple, actually. It has 3 steps. First one is the setup. Then we execute. And then we have the visualization. And the idea was to make this process super easy for everyone. So you don't need to know a lot to go there and execute the tool. So in the setup process, actually, what we have is you will generate an INI file, okay? So we have a command line in the tool to do this. And this file looks like that. Almost, you don't need to change a lot. I know that here looks a lot of parameters, but actually, you have to change few of those parameters. And basically, this setup file is divided in two parts. The first one is where you define the search space, for example, where you define the number of compute nodes, where you define the file size, where you define the OSTs, the number of OSTs. And the second part is how do you want to do the search? For example, you want to do a brute force where you do all the tests. You can define, for example, the number of repetitions. Okay, everything is very well explained in the README file. And then we have the execution part, where you basically will call the tool again, and you give the setup file. So in the execution part, what actually happens is the tool goes there, and it generates all the batch files that you need to execute those tests, all those benchmark tests. As a benchmark, right now we give support to IOR, so people that work with the I/O probably know a lot about IOR, but IOR is a I/O benchmark. And then IOPS goes there and manage all the execution of those tests. Go to Slurm, submit the first test, wait the result, go to Slurm again, second test, and so on. Then, in the end, okay. So then, what I want to show here now is actually what happens when we are executing and what we are executing. So in the setup file, we have those 2 lines that's called tests and IO pattern. And here, what you actually are defining is exactly what you want to characterize. So for example, if I have a line like that, computing stripe file size, computing stripe file size, what I'm defining is, for this IO pattern that's sequential share, so it's several processes writing to the same file, I want to characterize what happens when I change the number of computers. Then I want to characterize what happens when I change the number of OSTs, and then finally the file size. And I do it again. And you understand why I define it twice in this example. So the first thing that happens during the execution in this case, in this specific example, and one thing that you have to have in mind is that the user is the one defining the sequence of the tests. Okay, so we don't say to you, the best sequence is this one. Actually, we give you the blocks of tests, and you decide the sequence that you want to do. So the first test, we call it round, is compute nodes. And then we start by the default parameters. And again, you define this in the setup file. In this case, the default parameter was 4 SCTs, 1 gigabyte, 32 process per node. And then we do the search, right? We go there, we execute the benchmark, we do a lot of tests, and then after the first execution, the first round, we get the average maximum bandwidth. And that will decide the parameters that we will use in the second round. So in the second round, now I know that the maximum bandwidth, the average maximum bandwidth, is with 16 nodes. So then I go to the second round. The second round is number of OSTs. And then, now that I know that I need 16 nodes, I go to the number of OSTs. And I found that in this system, the average max bandwidth is actually with 7 OSTs. So I go to the next round. And I want you to see that we are increasing the bandwidth, right? Because we are searching to increase it. We are looking parameters that will maximize the bandwidth. So in the third round is the file size. I do the same test. And now I found that with a file size of 26 gigabytes, I have my average maximum bandwidth. Okay, so now the question is this the maximum bandwidth for this I/O pattern in this system? Maybe not, because the first time I test the nodes, I was using 1 gigabyte and only 4 STs. So that's why I'm doing a second round. So I finish the compute in the stripe in the file size, and I'm going to execute compute nodes again. In this time, in this case here, in this route, I don't have other compute nodes, more compute nodes to explore because I already using the max, so I keep the 16. In the 5th round, I look to the number of OSTs, it's 7 again, and finally, the file size. So now we have a full characterization for this I/O pattern to this, in this machine, right? So what we have that to have the peak performance using this an application with these characteristics, we would have to use 7 OSTs, 26 gigabytes of data, 32 process per node, and 60 nodes. Is that the max bandwidth on this machine? Probably no, because I didn't let the application explore all the parameters. So I have more computer nodes there, so I could keep searching. So another question is how long it take? So in the total, for this example that I show, it took more than 1,800 tests. In terms of time, execution time in the machine was only 2 hours. But the wait time, all the time, the moment I start the execution until the end was 3 days. Why? Because I actually put this to execute on last Saturday. And right now, it's the end of the year. So everyone in my lab, so this machine is in Bordeaux, all the students are running to get the machine and run the applications because they have to submit the thesis in April. So the machine is full. So can you imagine if I want to do the same by hand? I had to go there and see, do I have space? My application is still waiting. So that's actually one of the advantages of the tool. I don't have to worry about it. I put to execute. In the end, I have the results. So finally, we have also the visualization. So what we have in terms of visualization? We have all the graphs that I showed to you. We have the CSVs. And we have a report. Is it a nice report? No. Okay? It's ugly. I did it. But in 2 weeks, we will have a very nice report because I have a student work on it right now. And what's the idea of this report? So the idea is you have a machine, a cluster, and then you execute this tool. And that report should be in the documentation of the cluster because everyone that needs to have information about, okay, what happens in this machine when I go there and I use an application with that number of nodes, with that number of process, with this pattern, and that should be in your documentation, okay? Yes, I did that in 1 night. It's actually good for 1 night. Okay, so conclusions. The tool that I present, very nice, very well made. I/O performance characterization, also nice. Everyone should do. HMLA reports, not everyone should do it. And what are we going to do next now? So there is a machine in Brazil called Santos Dumont, and right now they are changed the storage system. They are actually change almost all the machine, increase it. So this machine is actually the biggest one in South America. And then we have a project with them, and the guy that's actually taking care of the machine, he's very interested in having this report as an information in the website of the machine. So he actually start to look to our tool and say, okay, I want to execute this before we start to have users on the new machine, but I need this. And he gave me a huge list of things that he wants. Different I/O patterns, you want to do search with process. So we have a list of features that we have to add until January. So to be a big commit, let's say. We also want to reduce the number of tests and reduce the time to execute those tests. So we are exploring some optimizations, for example, Bayesian optimization. We want to add new features. For example, one of the things that Franciele, that I will present her in the last slide, had in mind is actually to have a heat map showing the performance for each OST. In that way, you could identify, okay, look, this OST here is actually very slow compared with the other ones. And so you have a kind of a problem, right? So we want to add this as well, and a lot of things. So these are the other persons that work with this tool. Mahamat is probably the one that is doing everything. This is our engineer. Franciele is the one that's thinking about several things, and I am I. I'm the one presenting. Okay, so you have questions? So that's a good question. Okay, so if we come back to this file, you see this line here, stripe folders. So it turns out that the way we decide to do the tool is we don't give supports to different parallel file systems. It doesn't matter the parallel file system. The results that I show is actually in BGFS, but we have results with Lustre as well. What matters is if you want to do the test with the striping configuration, you have to go there in your parallel file system, create different folders with different stripe configurations, and that's exactly what I have here. I have one folder for each number of OSTs. So I have one folder that has one OST, two OST, three OST. So what you give to the tool is actually a list of folders. And the tool will you explore these folders. It doesn't matter what the folder means. What matters is I have the list of folders and I have to execute one test in each folder. And then you know, in my case, for example, I know what those folders means is the number of OSTs. So that's the way we decide to do it. And in this way, we don't have to give support to a parallel file system. You only have to provide folders. It's a good decision, right?
Yeah. All right, any other questions? All right, I'll ask a question. You made a comment saying that you didn't like the current output.
The what?
The current HTML.
Yes.
Can you go back to that and give us an idea of what you think the limitations are and how you're making it better? Because I think that might also help people think about this a little differently.
Okay, so the problem here is that I did a test. I asked some of the students to look to this and say, what you see here? Without giving any information to them. Just say, they are students that work with me, so they look to this and they know that it's something related with I/O. They look to this and say, I don't know, it's a bunch of numbers. I'm not exactly sure what that represents. So we don't have the information we need, right? We need to put more information here. We need to say, okay, so these numbers are actually the parameters that you need to reach the peak performance with this specific application, with these characteristics. And that's what we are doing now, actually, Jay, because we have a very nice, it's not finished yet, but we have a very nice report. And this report actually gives all these informations that we need. And one thing that this actual report do is that when you want to see one of the parameters, a specific case, you cannot go there, click on the graph, and go with the mouse and say, okay, what that point represent? And the new report will do this. So if you want to know exactly, okay, what represent the one of the points that we have here in the file size. Okay, so you know that that was executed with the number of compute nodes, process. So it will be way more informative in terms of quality of data, let's say, representation.
All right, let's thank our speaker.
Thank you.